This is an introduction to AutoEncoders. We will talk about the task and structure of AutoEncoders, undercomplete AutoEncoders, and the relation of AutoEncoders to PCA. Autoencoders are special kinds of neural networks which can be used in unsupervised learning tasks to learn a lower dimensional feature representation from unlabeled data. So, given the unlabeled data, the task is to learn a compression of these data. The autoencoder is a neural network consisting out of two parts. On the one hand, an encoder, which learns the mapping from the data, called X, to a low-dimensional latent variable, Z. So this first part of the neural network can be seen as a function, here called enc of X, the encoder of X, which returns us a low-dimensional latent variable, which is the feature representation we aim at. And the second component is a decoder, which learns a mapping back from this low-dimensional representation Z to a reconstruction of our input, which we call X hat. So this is the output of the second part of the network, the decoder. The loss function is usually one that compares the quality of the reconstruction of the input to the input. So we have a loss function that takes as one argument the input and as a second argument the reconstruction of the encoder. So this is one that we give X as input, encode this with the encoder part, and decode it then with the decoder part. And by this getting the reconstruction of our input. So this loss function tries to give us a reconstruction of the input. So we give an input to our neural network, and the output is again a reconstruction of the input. And the loss function compares both of these. But the internal goal is it to learn a good representation Z in the middle. This is also referred to as code. The computational graph in autoencoder looks like the following. We have our input, X, which is mapped by the encoder to our code or latent representation we want to learn, Z. And this is mapped back with via the decoder to our reconstruction X hat of X. Now we come to a special form of autoencoders, the so-called undercomplete autoencoders. A naive implementation of an autoencoder would be that we take such a 3-layer neural network with inputs, one hidden layer, an output layer, and take exactly the same number of neurons in each layer. With such a network, we could learn a perfect reconstruction, but it would not be useful at all. Maybe you can pause the video for a moment at this point and think about what could happen. If we have as many hidden as input neurons, what could happen is that we just learn a weight 1 at this connection between input 1 and hidden neuron 1 and set all the remaining connections from the other input neurons to hidden neuron 1 to 0. So this blue arrow would be, or the connection of this blue arrow would be 1 and all the grays would be 0. You would do the same for the second. So, and so on. So we would exactly copy the values of the input to the hidden layer. And then we could do the same in the decoder, mapping the state of the hidden neurons to the output. Again, we could exactly copy with weights of 1 from each neuron to the corresponding output neuron, the values from the hidden to the output. So we have a perfect reconstruction by learning the identity mapping, but we did not learn any useful representation Z in the middle. So this is for sure not what we would like to have. So an easy way how we can enforce a compression would be to just decrease the number of hidden neurons. That is, we would use a lower dimension of hidden neurons compared to the dimension of input neurons. An autoencoder with such a property is called undercomplete. And since we have a smaller number of hidden neurons in the middle, this is often referred to as bottleneck. This bottleneck of fewer neurons in the hidden layer enforces the autoencoder to capture only the most salient features of the training, and thus to learn a compressed representation of the input given by this hidden layer, the code. As neural networks in a supervised setting, we can train this autoencoder by minimizing the empirical risk with respect to some loss function, and we use a loss function that penalizes the reconstruction given by our autoencoder for differing from our input X. So we can use the mean squared error or squared error loss, or also called L2 loss, where we just measure the difference between X and the output of our autoencoder. This is a typical choice of loss functions, but other options are possible as well. For optimization, we can also use the same optimization techniques that we've had used before, for example, for feed-forward neural networks or convolutional networks or recurrent neural networks. That is, we could use stochastic gradient descent or its variants like ARM-SPROP or ADAM. So now we come to a small example where we train the MNIST data that we have already seen by now with an autoencoder. So we try to learn a good compression of these images of handwritten digits, which are given an input. We use some simple encoder to map this input to some hidden code, and a decoder to map it back to the image space. And we will, in this experiment, we will vary the size of the hidden layer, so the number of hidden neurons that we use, and see what the effect of varying the size of this bottleneck is. So this is a simple architecture we use. We have a 784 input neurons. This is exactly the number of pixels that one would need to represent these images of handwritten digits. And we have M hidden neurons in the middle, and then map back to the 784 pixels. In the first row, we see the original images, and in the second row, the reconstructions. If we use exactly as many hidden neurons as we have input neurons, then we get exactly what we have imagined what could happen. We get an exact copy from the input. So we see that really every single pixel, even small little details, are exactly the same as in the input. So we learn an identity mapping. If we now start to decrease the number of hidden neurons, the mapping is still quite good for 256 hidden neurons, but there is not perfect, or not identity mapping. It's not a perfect reconstruction anymore. We see little differences in the pixels, as for example here compared to here. If we further decrease our hidden neurons, now for 64, we still get quite good reconstructions, or super good reconstructions, where we have to look for the differences. With 32, we maybe the digits get a little bit blurry like here, but it's still quite good to interpret, or clearly to see which digits each image shows. And with 16, things get unclear. And if we reduce it further, it's even not clear anymore if this is a 3 or 8. So there's we need a certain number of hidden neurons to get a meaningful reconstruction. This gets even more severe if we reduce it further. So with only one hidden neuron, as we would expect, we get just only some kind of average number as a reconstruction. Now, a simple way of increasing the capacity of AutoEncoders is to add more layers. So up until now we had just simple neural networks, 3-layer neural networks with input, hidden, and output layer, where we just had the setting that input and output, or input and label, are the same. And now we can do the same as we had before with feed-forward layers. We can add hidden layers. So we could have an extra hidden layer here in the encoder, and another extra layer here is a decoder. This, of course, increases the capacity of the neural network, and such could lead to better compressions here in the middle. And this would be the code that we are interested in. Now we come to the point that autoencoders can be seen as some kind of principal component analysis. Principal component analysis was shortly mentioned in the introduction to unsupervised learning, and it's a well-known technique used in machine learning and statistics in general. And for those of you who don't know it, I could recommend to briefly look it up. It's a good technique, or a good and simple and well-known technique for dimensionality reduction. But now let's look at an undercomplete autoencoder with some special properties. First, we require this autoencoder to have a linear encoder function. This is, we require the activation function used in the hidden layer to be linear, or we don't use any activation function there. And we have a linear decoder, so we also don't use an activation or a linear activation function in the output layer. This means that we can learn just linear mappings from our input to our hidden space and back to our output space. We train this autoencoder again with the simple L2 loss, or squared error loss. And we have, before we train the model, we require the inputs to be normalized so that they have zero mean. So training this autoencoder with the L2 loss just gets equivalent to the task of learning a linear projection of the data with a minimal L2 reconstruction error. Now it can be theoretically shown that the optimal solution to this task of learning the linear projection with the minimal L2 reconstruction error, that the optimal solution for this task is given by an orthogonal matrix, so an orthogonal transformation, which is given by the k singular vectors with the largest singular values, and k is set is equal to the number of hidden neurons. So to find the weights of the encoder in this encoding part, the weight matrix, these weight matrix would be orthogonal, and the rows or columns would exactly correspond to the singular vectors. Mathematically, you probably all recall that with this orthogonal transformation, we perform a coordinate system rotation. And in this simple example where we have a three-dimensional space and we just focus on two coordinates because we want to have mapping from R3 to R2, then these two-dimensional coordinates in the three-dimensional space are rotated to give our latent feature space, and if we map it back, we map these back in our original space, three-dimensional space here. Interestingly, this is an equivalent formulation to principal component analysis, often shortly denoted as PCA, where we also use an orthogonal transformation. But we aim at converting a set of observations of possible correlated variables into a set of values of linearly uncorrelated variables. And these linearly uncorrelated variables are called principal components. So there we're searching for some kind of rotation that uncorrelates our variables. And the transformation is defined in such a way that the first principal component, so the first latent variable we map to, has the largest possible variance. So it should explain as much of the variability in the data as possible. After we have that, we are searching for the next component that explains as much as possible from the remaining variance. So if you never heard of principal component analysis before, that may be a bit difficult to understand, but the take-home message is here that the both formulations that we have are equivalent. Find a linear projection into a k-dimensional space that minimizes the L2 reconstruction error, as we have it for an autoencoder with a linear encoder and a linear decoder, and maximizing the variance of the projected data point, which we have in the statistical formulation of PCA. So the take-home message is, if we have the special kind of an autoencoder with a linear encoder and decoder, and we have a L2 reconstruction error or L2 loss for training, and do this kind of normalization in the beginning, then training an autoencoder is equivalent to something which is well known in statistics and called principal component analysis. And what we can take from there is that if we take a nonlinear decoder and encoder, which is usually the case because we usually don't use linear activation functions in neural networks, as we all know by now, we get something which can be seen as a nonlinear generalization of PCA.